everyone, welcome to the lecture today. Today we will go through the last part of the soil property. Previously we showed the soil classification, presence of clay, and the mechanical properties of the soil, including the modulus of reaction and the resilient modulus. We actually have some additional materials for the mechanical properties. So now let's recall the mechanical properties of soils that we listed in the previous lectures. We have already gone through the stiffness of soil, including coefficient of reaction for subgrade soils, Poisson's ratio, and the resilient modulus MR. And we found that MR is a linear or nonlinear functions of bulk stress and deviator stress. In this class, we will try to check the California bearing ratio, CBR, and the test to get the CBR value. Also, for the permanent deformation resistance, the details about this part will be discussed in the asphalt technology in the future. Let's first go to check California bearing ratio, CBR. It's actually defined by the experiment ASHTO 193. It provides the measurement about the soil property in strength, ductility, and moisture susceptibility. However, CBR is not a soil property. It's actually an index of the soil by comparing with the standard material. CBR provides an indication to the soil's response to confinement. It actually will measure the combined effect of the stiffness and the strength of the soil. The equation here shows how we will calculate the CBR values from the experiment. During the CBR experiment, we will actually do the penetration to the specimen and then measure the load carried by the specimen at 2.5 mm penetration. The CBR is defined as the load carried at 2.5 mm over the load carried by standard crushed rock base times 100. For the unit of PSI, which would be the unit load over 1000, if we use the unit of kilopascal, that will be unit over 6900. The figure here shows the result from the CBR test. It will actually measure the unit load applied to the specimen under different penetration. The red line here shows the result for the standard materials, while the blue line is the specimen, which we shall observe from the test. In general, the result about the specimen should be lower than the standard material. If the granular material is applied as the base layer, the CBR value should be higher than 80. For sub-base layer, it should be at least 20. While for the clean gravel, it will be very hard to be compacted, so usually the CBR test is not appropriate for clean gravel materials. This page lists the procedure to conduct the CBR test. First, we have to prepare the sample for the test. The soil sample should be compacted according to the Proctor compaction procedure for the experiment. And if we want to conduct a soaked experiment, the sample should be soaked in the water for 4 days. And then every day you need to measure the swelling of the sample. Once the sample is ready, it will be placed in a loading machine and apply a 4.5 kilogram surcharge. And this surcharge is put on top of the specimen to reproduce the vertical stress at the top of the subgrade. Usually is 23 kilopascal, which will cost by 1 meter pavement layers. And then 15 mm piston will be attached to the specimen, and it's forced into soil specimen at a constant speed, 1.25 mm per minute or 0.05 inch per minute. In the test, you have to record the load applied to the specimen at every penetration, and the load applied at 2.5 mm penetration is used for it to calculate CBR value. In the calculation of the CBR, we have to know the load applied for standard material. The table here just showed the load for standard CBR material at a different penetration. At 0.1 inch penetration, the load should be 1000 psi. At 0.2, it's 1500 psi. You will observe that with a larger penetration, the load should be larger. However, the increment in load will be smaller at a higher penetration. The table here shows that the CBR values for different groups of the soil. Actually, for the A1 soil from ASHTO method and the GWSW, GP, and GM from USCS method, the CBR values are usually higher than 70 and is in a very good subgrade materials. For A2, A3 from ASHTO, SW, SP, SM, and SC from USCS methods, the CBR varies from 20 to 70, and it makes a good material for subgrade. If the CBR is between 5 to 20, it means that the soil is actually weak for subgrade, and if it's less than 5, it's very poor. In that sense, you have to consider remove the soil or do some process about the soil, such as compaction or mixed with additional materials to increase the CBR values. From empirical analysis, we can find out the relationship between resilient modulus and the CBR. The equation here actually provided by ASHTO in 1993. It shows the relationship between MR and the CBR with nonlinear and linear models. If we apply the unit megapascal for MR, then we can find that MR would be 17.6 times CBR to the power of 0.64, or with the linear model, 10.3 times CBR. If the unit is PSI, then MR is 2555 times CBR per 0.64, or 1500 CBR. And you have to remember that this model is only applied for the cross-clean non-plastic materials with CBR less than 100. If it exceeds that value, the model will not be appropriate. The figure below shows the result from the linear and nonlinear model about MR and CBR. You can see that the pattern about the relationship from these two models are fairly close to each other. But we have to carefully apply this relationship because this one only comes from the empirical analysis, and there isn't any mechanical analysis about this relationship, so it may not be suitable for many other types of soils. There are actually many models describing the relationship between resilient modulus and the CBR. We already checked the ASHTO model, the CSIR, the Council of Scientific and Industrial Research assumed that MR as a function of the CBR as 20.7 times the CBR to the power of 65. This one is very similar to ASHTO model, but it has different coefficients. US Army Corps of Engineers had a different model. MR is 37.3 times CBR to the power of 0.71. In UK, the linear model proposed by ASTO is applied for clay, MR equal to 10.3 times CBR. This model is only applied for fine-grained soils and fine sand with the CBR less than 20. It's not applied for the granular materials. And in their applications, the coefficient, which is 10.3 here, will be varied based on the soil types. It could vary from 5 to 20. For granule-based and sub-based soil, we don't have a very good model, but we can see that there will be a lot of factors affecting the relationship between MR and CBR. We know that MR is a function of the bulk stress and deviator stress, and for CBR is affected by the texture, density, and water contents of soil. If we try to see the ratio between MR and CBR, we can find that it is a function of a lot of variables. The two figures below shows the histograms of MR over CBR and MR over CBR to the power of 0.64. We see that the pattern is very similar to each other, which means it's possible for us to find out some empirical model to describe this relationship. First, let's check the two most important variables for the MR to CBR ratio. The figure here shows the data points observed in reality for the MR to CBR and the different back stress and the water contents. In general, with the fixed water content, we can see that there's a linear relationship between MR to CBR ratio and the back stress, which means it's able for us to find out a linear model to describe this relationship. Also, we can observe that with higher water contents, the MR to CBR ratio will be smaller, and that means that the stiffness or strength of the material will be smaller. In addition, we can also explore the relationship between CBR and the modulus of the subgrade reaction from the empirical data. And the figure here below actually shows the values of different CBRs with respect to different modulus of subgrade reaction. You can see that roughly if the CBR is around 80, the modulus of reaction for the soil is 700. Also, in general, with higher CBR values, the modulus of the subgrade reaction would be larger. However, it would be very hard for us to find out a well-defined model to describe the relationship between CBR and modulus of reaction. It all comes from the empirical data only. This table summarizes the recommended values for the modulus of reaction and the CBR for different types of the soils. For example, you can see that for A1A soil, well-graded soil, the CBR varies from 60 to 80. For the modulus of reaction varies from 300 to 450. And for finer material, such as A4 silt, the CBR is around 4 to 8, while for the modulus of reaction, it's 25 to 165. Now let's make a quick summary about the California-Bellman ratio. Actually, CBR is used to classify and evaluate soil subgrade and base course materials for flexible pavement instead of the rigid pavement. And the CBR test is actually an empirical test. The result from the CBR test cannot be accurately related to any fundamental properties of the materials, such as the modulus of resilience or the modulus of the subgrade reaction, but we can build some empirical models to describe the relationship. The last soil property that I want to introduce in this class is shear strength. Shear strength is actually directly related to shear failure in soil, which is caused by the slippage of the soil particles past each other. And the resistance against the shear failure is just the shear strength. Usually the shear strength is measured with the friction and cohesion. Both of them will be defined in the next few pages. In order to measure the shear strength of the soil, we need to recall the triaxial compression test. And this test will measure the shear strength under different controlled drainage conditions. In the test, it will prepare a cylindrical specimen of the soil, and this specimen is subjected in cases in confining fluid or air pressure. And then axial load will be applied for the specimen until it fails. In addition, the test is called a triaxial because we know the three principal stresses applied to the specimen. This page shows more details about the triaxial compression test. The figure on the right shows the load applied to a cylindrical specimen. During the shear, we can see that the major principal stress, sigma 1, is actually equal to the applied axial stress plus the confining stress sigma 3. The applied axial stress is defined as the actual load applied to the specimen P over the areas of the cross-section A. So sigma 1 is delta sigma plus sigma 3. For the applied axial stress, it is termed the principal stress difference, or sometimes we define it as the deviator stress. In the test, we also have the intermediate principal stress sigma 2 and minor principal stress sigma 3. They are demonstrated on the figure at the right bottom, which would be a cube picked from the cylindrical. In this test, sigma 2 and sigma 3 are identical and they are the same to the confining stress. Now let's see the triaxial compression test for sand material. First, we will prepare a sand specimen, and it will be loaded to failure under restrictive and confining pressure, 15, 30, and 45 psi. During test, we will try to record the relationship between the stress and strain. In the test, the failure is defined as the time when we reach the peak, or 3 maximum value of principal stress difference. Finally, the test will be stopped when the load peaks or drop down about 20% to the peak value. Now let's see how to process the data from the test. The figure on the left actually shows the stress-strain relationship and the different confining stress we defined in this test. In the test, we assigned 3 confining stress, 15, 30, and 45 psi. Each line in this figure represents the result with 1 confining stress. So first, let's check the first confining stress of 15 psi. And we know that the confining stress is sigma 3. In the curve, we can find out the maximum axial stress as delta sigma A. Then we can calculate the major principal stress. We say as sigma 1A as delta sigma A plus sigma 3A. And for the confining stress of 15 psi, we get a 1 maximum principal stress. And with these 2 values, sigma 1A and sigma 3A, we are able to draw a Mohr circle. This would be in a half circle in the shear stress and normal stress region. Similarly, for the second confining stress, 30 psi, and the third one, 45 psi, we can get another 2 more circles. For these 3 more circles, we can draw a line which will tangent to all the circles, and the relationship between the shear stress and normal stress along this line will be shown in this equation. And in this equation, we have 2 coefficients. The first one is C. C is actually defined as the cohesion, which we specified in the previous pages. And the second one is phi. It actually represents the slope of the line. So that would be the angle. It's actually defined as the friction angle. With these 2 coefficients, we can find out the shear stress as the function of the normal stress. And the C and phi are actually applied to measure the shear strength for the material. With that, I would like to summarize the triaxial compression test with several questions. First, are the cohesion and friction angle generally required in pavement structure design? The answer is yes. Both cohesion and friction angle is highly related to the determination of shear strength. And the shear strength of the subgrade is very important for the pavement structure design. Second, given a sand of a certain density, is the friction angle of soil constant? The answer is mostly no. Actually, the friction angle on the soil is determined by the soil contents and the density. So there are two factors. The soil contents will be related to the grain size distribution, which will related to the percentage of different size of the particles inside the soil. So if the contents of the soil is different, then the friction angle can be very different. Third, what if the density of the sand is increased? In general, if the density increase, the friction angle will also increase. This would be a general trend, or if it could be more complicated based on the consideration of the soil content. So that will be all about the lecture today. Thank you very much for your attention.